Okay, so welcome back. Today we are going to talk about least squares and optimization. And to start, I just want to do a quick recap of where we were last time. So we started off by saying that we had labels that we store in a vector y, and it's length n for our n training samples. And we have features that we've put all in a big matrix X, and that matrix is n by p because we have p different features. And we are going to assume that n is greater than or equal to p, and that the rank of x is equal to p. So as we talked about last time, all of these different features stored in this feature matrix are linearly independent. And we want to find a weight vector w so that some predicted weights y hat equal to xw are as close as possible to our observed labels y. And we've talked about this in a least square sense. So pictorially, we have this vector y hat, and we are going to have that be equal to this matrix of features x times a weight vector w. And in this picture, the height here, n, is the number of samples. So that's both the height of y and the height of x. And the width of x and the height of w are both p for the number of features. So that's the scenario that we talked about last time. So to start off, what I would like to do is, first of all, talk about this in the particular setting of classification. Let's imagine that our yi's, our true labels, aren't just real numbers, but they actually can only be +1 or -1. So for instance, in our example where people are smiling or not smiling, we have +1s for smiles and -1s for not smiles. And we said that we're going to compute our weight vector w hat as being the argument w that minimizes the sum of squared errors. So we want to minimize the distance between y, our true labels, and xw, the model, the labels that we predict using this linear model. Okay. And so then we said that under these conditions that I laid out here, that w hat was going to equal x transpose x inverse x transpose y. So this is what we derived in the last lecture. And so now the question is, how do we use this within a classification setting? So what we could do is we could let y tilde, our predictions, or wait, we said y hat is equal to xw hat. So we called those so far our predicted labels. But the elements of y hat are not labels. So we're not getting a bunch of plus and minus ones here. We're actually getting real numbers. So for one sample, y hat might be 0.5, and for another sample, it might be negative 0.7. And so now what we'd like to do, though, is to actually make a prediction. Like, is this a picture of somebody smiling or not? So once we've got this y hat, what we have to do is come up with a classification rule where we're going to say we predict +1 if y hat I is greater than 0, and -1 if y hat I is less than 0. In other words, what we could do is we could define some y tilde I, which is equal to the sign of y hat I. And so now this is actually going to be a label. It's going to be a +1 or a -1. And so now we can actually see not only if y hat is close to y, but whether the labels that we're predicting equal the labels that we actually observed. So this is how we could actually come up with predicted labels. And once we have that, then we can even start to think about taking a new sample, like a new photograph, and we'll call that x new. So this is a feature vector of length p for our new photograph. And what we want to do is predict its label. So what are we going to do? We're going to say, first of all, y hat for this new sample is going to be the inner product of the feature for this new sample and this weight vector that we estimated using our training data. So we used our training data to find a good weight vector, and then we can now use that weight vector with our new feature to make a new prediction. And once we do that, then we can say that our y tilde new, so our actual predicted label, would be the sign, either a +1 or -1, of y hat new. And so this is the overall sort of pipeline of a classification system. We take all this training data, we try to learn a good weight vector in the context of this linear model, and then we take a new sample and we plug that learned weight vector that we computed with our training data into that linear model and use that to come up with a new predicted label. Are there any questions about that? Does that make sense? Okay, so hopefully that sort of just closes any gaps that we might have missed in the past. And now what I'd like to do is to talk about what we have right here. So what we said is that w hat is the value w that minimizes this length y minus xw, 2 norms squared. And then we derived this equation for w hat using this geometric argument. And what I would like to do today is to derive that same expression from a different way by thinking about it as an optimization problem. So instead of thinking about it geometrically, I want to think about it via optimization. And this is going to teach us a lot of stuff about optimization that we're going to be able to extend upon and build upon for other problems. Okay, so we said w hat is the argument w that minimizes this distance y minus xw. And what I'd like to do before we go much further is talk a little bit more about these norms. So we said before that if I had a vector x and I computed its 2 norms squared, that was equal to the sum over I from 1 to however long the vector is, let's say n, of xi squared. So that was the definition we used last time. And one thing that we neglected to say was that this is also the same as x transpose x, the inner product of x with itself. And hopefully this is kind of obvious, right? So if we were to look at x transpose x, and x is a column, then what have we got? We have x1, x2 to xn times x1, x2 to xn. And what is that? Well, that's going to be x1 squared plus x2 squared all the way to xn squared, which is exactly the same as this Euclidean norm squared. Okay, so it's the same way of representing something different. I'm sorry, it's two different ways of representing the same thing. So here, now I can rewrite my optimization problem using that. I can say this is the same as y minus xw transpose times y minus xw. So I'm just using this concept here and applying it to this optimization problem that we're working with. And now I'm going to expand the square. And now we're working with matrices and vectors as opposed to working with scalars, but there's a lot of similarities. So if we expand the square, we first take the first elements of the two factors. So I've got y transpose times y. Then I'm going to take the two inner components. So I'm going to have negative xw transpose times y. Then I take the two outer components, and I have negative y times transpose times xw. And then finally, I have plus xw transpose xw. Does that make sense? Okay. And I can simplify this a little bit further. So y transpose y stays the same. When I have a product of a matrix and a vector, and I take its transpose, then that's going to, I'm going to take the transpose of everything in there, and then I'm going to flip the order. So I'm going to have w transpose times x transpose times y minus y transpose xw plus w transpose x transpose xw. Okay, and there's one final simplification that we can do, which is optional but maybe a little convenient. This is the same as the argument over w, y transpose y. These things in the middle here, these are scalars, right? Once I multiply y transpose times x times w, it's just a scalar. And so this scalar and this scalar, they're exactly the same number. And so this is just minus 2 times w transpose x transpose y plus w transpose x xw. Okay, so we started off by saying we wanted to minimize this sum of squared errors or sum of squared residuals. And now we have taken that objective function, that thing that we want to minimize, and we've rewritten it as this long matrix vector equation. And now what we want to do is we want to figure out how to actually solve that optimization problem. So before we do that, let's just do a little warm-up with a simple optimization problem in one dimension. So imagine I've got a function f of w that I want to minimize. I want to find the minimum point of this function. And let's let this function be 1/2 w squared minus w minus 1/2. So I can actually plot this function. So here is w, and here is f. And let's see, so I've got 1, -1, 1, 2, did I go to 3? Sure, 3. And then I think this is 1 and -1. And I think it's something like this. Okay, so this is my function f of w. And what I'd like to be able to do is to find w hat, which is the argument w that minimizes f of w. So we can eyeball this and say that it looks like it's equal to 1. But what's another way besides eyeballing it that we could use to figure this out? Right, we could take the derivative and set the derivative equal to 0. So we could take df dw, and df dw in this case is equal to what? Let's see, w minus 1. And we can now set that equal to 0, and that tells us that w hat is equal to 1, which is exactly what we drew on the board. Now we can do this because this is a nice bowl-shaped function, right? It's curving downwards. If instead it was more of a hump function, then we'd have a problem. So this is an issue that we're going to talk about as we progress here. But for now, we're able to just take the derivative and set it equal to 0 for a function like this, and that's going to give us the minimum. So now what we want to know is how can we actually go about solving optimization problems like this, where instead of optimizing over scalar numbers like a scalar w, we instead want to optimize over vectors, weight vectors. All right. So before we're looking at this geometric perspective, we said it was really important that x transpose x be invertible. And that's how we came up with our solution, which is a function of x transpose x. So something similar shows up positive when we think about the optimization perspective as well. And we're going to see this through the lens of positive definite matrices. So recall that we need x transpose x to be invertible. For our previous arguments to work out, turns out that's also important in an optimization setting. Okay, so the following two things are equivalent. For a matrix X that has n rows and p columns, where n is greater than or equal to p and the rank of X is equal to p. So the first one is that X transpose X is invertible. Or in other words, X transpose X inverse exists. And that is the same as saying that X transpose X is positive definite. Okay, so what do I mean by that? Let's go over here and write a formal definition. So we say that a matrix Q is positive definite and we abbreviate this as PD if we can take a vector X and compute X transpose QX, and that is greater than 0 for all X that are not equal to 0. And the shorthand is to say Q is sort of like curly greater than 0. So we're going to look at some examples, but I just want to put in a second part of this definition first, and then we'll kind of think about an interpretation. So a matrix Q is positive semi-definite PSD if X transpose QX is greater than or equal to 0 for all X not equal to 0. And here, the shorthand is Q curly greater than or equal to 0. Okay, so what I want to do is think about what this means and why we care about it. And we're going to see how relevant it is in two different ways. So first, let's look at a couple of examples. So let's imagine that we're just working in one dimension. So X is just a real number, and Q is just a real number. And so when we look at X transpose QX, all we really mean is that this is QX squared. And when is this greater than 0? So QX squared is greater than 0 no matter what X is, under what condition? Yeah, if Q is greater than 0. That's right. So for a scalar, it just corresponds to Q being positive. So what we could do is we could imagine minimizing some function f of x, which is equal to qx squared. Let's draw a picture. So here is x, and here is qx squared. And so my function would be this nice little parabola like this. And this is easy to minimize. And what I mean by that is that it is convex. For the purposes of right now, all I mean is that it is sort of bowl-shaped. But another way of thinking about convexity is that for any point on this curve, what I could do is I could compute its tangent. And if I look at its tangent, the function is above the tangent. And that's true anywhere on the function. No matter what tangent I compute, the tangent is always underneath the function. And so there's a lot of rich optimization theory about how to actually find minimizers of convex functions. So we've got good tools that we can use to minimize this. They work well in a variety of settings, and it's just considered a very favorable scenario. And in contrast, if we had a setting where, Q was less, so in this case, Q is greater than 0. And in contrast, if we had a plot of qx squared where Q is less than 0, then our function looks like maybe some upside down parabola. And now optimization starts to seem more difficult. So first of all, this is no longer convex, right? If I look at tangents of this curve, my function is not above the tangents. That's a maybe formal way of thinking about convexity. But just from looking at this picture, right, this is not a function where we can compute the derivative, set it equal to 0, and have that point be the minimizer, right? It's the maximizer. The curvature is going in the wrong direction, so it's harder to find the minimum point. So this is an example where it is hard to minimize or non-convex. So at least in this scalar setting, how easily we can find the optimum or the minimizer of a function is related to whether we have a positive definite Q or not. So now what we want to do is think about this in 2D instead of 1D. What happens when Q is a matrix instead of a scalar? Okay, so for example, X now is a length 2 vector, and Q is a 2 by 2 matrix. So if Q were equal to 1, 0, 0, 1, so this is simply an identity matrix, which we talked about last time, then again, we could start to think about trying to minimize a function f of x, which is x transpose qx. And let's make a plot of that. This is a little trickier. Okay, so we've got the horizontal plane. So this would be like x1, and over here we've got x2, and up here we've got f of x. And so now our function is an actual kind of 3D bowl. Hopefully that looks something bowl-like. And so again, the intuition that we had in the scalar case should carry over here. So when Q here is positive definite, then we have a function f that is easy to minimize or convex. And in contrast, if Q were equal to -1, 0, 0, -1, then we'd be in the opposite situation. And in fact, sorry, let me just say a couple more words about this that I forgot to mention earlier. So if we expand this f of x, what is this? Well, all this is x1 squared plus x2 squared. Right? So this is a function that I can compute the derivative of with respect to x1 and x2. And ultimately, we're going to be able to see that the way we minimized this function over here, we can use similar ways to minimize this function over here, because q in this case is positive definite. Right? So this is going to be greater than 0 for all x vectors not equal to 0. So we've got a case where q is positive definite, and we end up with an optimization problem related to q that's easy to solve. Now, in contrast here, we have a different q, and if we were to look at x transpose qx here, this is negative x1 squared minus x2 squared. And is this going to be greater than 0 for all x? No, right? This is always going to be, in fact, less than 0 for all x that are not equal to 0. And if we try to make a picture of this, just like we did before, then all of a sudden we kind of have this upside down bowl. And again, we've got a carryover of the intuition from the scalar case to this matrix case, where, I'm sorry, what I'm drawing here is f of x, which is equal to x transpose qx, just like before. And again, we have a problem that's hard to minimize, because certainly the place where my derivatives become 0 is not the place that's the minimal point. So thinking about positive definite matrices gives us a lens into thinking about how we're going to solve this optimization problem associated with least squares, and when we're going to be able to find a good solution versus when finding a good solution is hard. Okay, so let's talk about some properties of positive definite matrices. So the first one is if I've got a matrix P that's positive definite and another matrix Q that's positive definite, then their sum, P plus Q, is also positive definite. And I want to just sort of prove that to you, because I think it helps us kind of connect our understanding of what's going on with these positive definite matrices with the definition. So if P is positive definite, then it means x transpose Px is greater than 0 for all x not equal to 0. And likewise, x transpose Qx is greater than 0 for all non-zero x. And so the question then is P plus Q positive definite or not? So in order to look at that, we would look at x transpose P plus Q times x. And now what we can do is we can expand that. That's x transpose Px plus x transpose Qx. And we already established that both of these are greater than 0 for all x that's not equal to 0. So properties like this just pop out very naturally and very simply from the definition. And similarly, if Q is positive definite and we have some scalar A which is greater than 0, then the product A times Q is still positive definite. And you can prove that similarly in a straightforward way. And I'm not going to do it now because we're running a little short on time. But again, we just kind of naturally plug in the definition. Now for any matrix A at all, square, rectangular, no matter what, if we look at the product of A transpose times A, that is always positive semi-definite. And similarly, A transpose is always positive semi-definite. And here's another one that's incredibly important for least squares. If we have a matrix A that is positive definite, then A inverse exists. Okay, so now what I want to do is talk about how we could use this positive definiteness and to better understand things about least squares. Come back to that. Okay, so recall our optimization formulation. Where we said that the weight vector we want to find is the argument W that minimizes Y transpose Y minus 2 W transpose X transpose Y plus W transpose X transpose XW. Okay, so now what we want to do is we want to think about trying to solve this optimization problem. And right off the bat, what can we say about this? X transpose X that's showing up in our optimization problem. So property 3 of positive definite matrices. What can we say here? So remember, we said for any matrix at all, here we wrote it as A, that A transpose A is going to be positive semi-definite. And so here, what we know is that this is definitely positive semi-definite, without even really thinking about it. Okay. Now what we're going to do is we're going to tie all this stuff together. So we are going to assume that X transpose X not only is positive semi-definite, but it is positive definite. And what that means is that this f of W, which is equal to Y transpose Y minus 2 W transpose X transpose Y plus W transpose XW. That function is convex. And so in analog to what we talked about in the 1D case, we can compute the derivative and set to 0. only we're not really dealing with scalars anymore. We have vectors. So instead of derivatives, we use gradients. Okay, so what do I mean by the gradient of a function? So the concept is very simple. So I take a function f and I write its gradient using this triangle, and I write a little w there to indicate we're computing the gradient with respect to the variable w. And this is like computing the derivative with respect to w in the scalar case. And all I mean by this is that I'm going to create a vector, and the first element is going to be the derivative of f with respect to the first element of w. And the second element of the gradient is the derivative of f with respect to the second element of w, all the way down to the derivative of f with respect to the pth element of w. So when we talk about a gradient, we're just saying we're going to make a vector that corresponds to the derivative with respect to every single different element of w. Very, very simple. Okay, so what I want to do is come up with a few examples of different functions and gradients that are very important. And once we do that, we will know exactly how to solve our least squares optimization problem, and we'll be done. Okay, so let's say, for example, that my function fw is equal to some vector c, inner product with w. So remember, this is just c1 w1, c2 w2, all the way to cp wp. And now what I want to do is I want to compute the gradient of this function with respect to w. So first thing I do is I say, well, what's the derivative of this function with respect to w1? And that is what? c1. Excellent. And then the derivative of this function with respect to w2 is c2, all the way down to cp. So the gradient of the inner product of w with some other vector is simply equal to that other vector. And notice that the size of the gradient is always equal to the size of the vector that we're computing the gradient with respect to. Okay. Another example. Let's imagine f of w is equal to w transpose w, or the 2 norms squared of w, which is w1 squared plus w2 squared, all the way to wp squared. So again, we just compute all these derivatives one by one. So the gradient of f with respect to w is 2 times w1, 2 times w2, 2 times wp. So, summary so far, the gradient with respect to w of the inner product of c and w is simply c. And the gradient with respect to w of the 2 norms squared of w is simply equal to 2 times w. And hopefully this feels natural and consistent with your understanding in the scalar case. Because if I just had, some function, if these were scalars, I just have a constant times my variable w, then the derivative is simply the constant, right? And if w were a scalar, so my function is just w squared, then the derivative is 2w. And here we've got the same thing, 2w, it's just a vector instead of a scalar. Okay, so we just need to figure out one more example, and then we're going to be able to handle least squares. Ah. Okay. So f of w now is equal to w transpose q times w. And we want to compute the gradient of this. So let's just write out what this is first. This is the sum from I equals 1 to p, and the sum from j equals 1 to p of wi qij times wj. All right, so now in order to compute the gradient, we need all of these different derivatives. So let's compute the derivative of just one term in this sum before thinking about the whole sum. So what's the derivative of wi qij times wj with respect to wk? So we want to think about what that derivative is, and there's three possibilities. One is that k is equal to I, and that's equal to j, that all these three things are the same. Another possibility is that I is equal to k, but they are not equal to j. Another possibility is that I is equal to is not equal to k, but k is equal to j. And then a final possibility is that k is not equal to I and k is not equal to j. Okay, so if k and I and j are all equal to one another, then what is this derivative? So this would be 2 qii times wi. Right, very good. Now if I is equal to k, but not j, then what have we got? So then this w is, oh, what? Right, qij wj. That's right. And then if I is not equal to k, but k is equal to j, then we have qij wi. And then finally, if k is not equal to I or j, it's just 0, right? Okay, so in order to figure out the gradient, then what we have to do next is figure out the derivative of f, the sum of all of these terms here, with respect to dwk. And that is simply the sum from I equals 1 to p, sum j equals 1 to p, of the derivative of wi qij wj dwk. So you can work this out on your own. It's not hard. It just involves a lot of bookkeeping, figuring out all the different terms that you have where. And so it's a little tedious, but like I said, not difficult. But then from there, what you can derive in a pretty straightforward way is that the gradient of this function is equal to q times w plus q transpose times w. And if q is symmetric, that is, if q is equal to q transpose, then this simplifies to be that the gradient of f with respect to w is 2qw. Okay, so I just have one final point that I'm going to make today. And basically what we're going to do is we're going to use these three examples that we just computed in order to solve the optimization problem for least squares. Okay. So now f of w is equal to y transpose y minus 2 w transpose x transpose y plus w transpose x transpose x w. And now what we want to know is what's the gradient of this. So the gradient of the first, well, let's do it one term at a time. So for the first term, y doesn't depend on w at all. So the gradient of that with respect to w is just 0. For the second term, we've got w transpose x transpose y. So which example does this remind us of? Right, the first example where we had a constant inner product with w. So in this case, it's sort of like our constant vector c is negative 2x transpose y. And so we said the gradient of the inner product of w and a constant is the constant. And so we're just left here with negative 2x transpose y. And then for the third term, how can we figure out the gradient of that? This is like example 3, right? Exactly. So if we think of q as x transpose x, which in this case is equal to q transpose, then we're just left with 2x transpose x times w. And now what we can do is we can set this gradient equal to 0. And that tells us that x transpose xw needs to equal x transpose y. And when x is positive definite, which we talked about earlier, right? So if this is positive definite, then we can take its inverse. And that tells us that w hat, the optimal value, is x transpose x inverse, x transpose y. And so we got exactly the same solution that we got in the last lecture using these geometric arguments, only this time we arrived at it in a completely different way using these optimization arguments, computing gradients of objective functions and setting them equal to 0. And we saw how using notions of positive definiteness allowed us to try to understand why having x transpose x be invertible is important. And in particular, what it's doing is it's ensuring that our objective function more or less has this definitely has this convex shape. And you can think about that as roughly being like this bowl shape, so that when we do take the gradient and set it equal to 0, that place where it flattens out is the bottom of the bowl and not the top of the bowl or something else that's irrelevant to us. And so what we saw is everything here in lecture 4 from a totally different perspective than in lecture 3, but leading to exactly the same place. And so next time what we're going to do is we're going to think more about how we can build on this and extend on it and use it to understand notions of positive definiteness and rank and how it all ties together. All right, thanks very much.